All right, let's take a look at the questions for checkpoint number 9 here. So got a few different related rates problems for you. So this first one's talking about a block of ice in the shape of a cube. So first thing I'm going to do here is draw a picture of what I'm looking at here. As always, my pictures are not great, but they're just here to kind of help me organize. So what do I know about this cube? Well, I know it's going to keep the shape of the cube as it shrinks. Um, so since it's going to keep the shape of a cube, I can make some assumptions here. So part A is asking for how fast the cube's surface area is changing. So um, maybe it's helpful if let's start from the very basics here. What are the things that we need? Okay. So for part A, let's take a look at what variables or quantities I'm going to look at. So one of them is clearly surface area. So the surface area of the cube, and that's going to be in some length squared, so centimeters squared. What other units am I going to have to worry about? So let's look at the question. Block of ice in the shape of a cube. As it melts, each edge of the cube is decreasing at a rate of, okay, so I'm going to call this variable L. So this is going to be the length of edge of cube. And since it's a cube, I know all those edges are the same length at any given time, or same length as each other. They're all shrinking, but they're all shrinking in the same way. So this is going to be in centimeters. I think that is going to be all I need for now. For now, and when I emphasize for now is because I see that this rate is given in terms of unit time. So that is going to come from when I need a derivative. But first, I can do this. I can make an equation for the surface area of my cube as a function of its length. So if every edge of this cube has a length L, so all the faces of a cube they're squares. So the area of the surface area of this cube is going to be length squared times the number of faces there are. Think of a die. A die is a cube, approximately. It has 6 faces. So the area, and I'll just call it A equals 6L squared. But the question I'm asked here is, how fast is the cube's surface area changing? Can I give a name to that rate that I'm asked for? So I want to know something about the change of the surface area. So I think I'm looking for dA, so change of area, but with respect to what? So keyword I'm going to focus on here is fast. So that signifies to me that I'm going to be looking at something in terms of time, or something that varies with time. It's also kind of implied by one of the rates that I mentioned here before. So we know that the edge of the cube is decreasing at this rate, 2 centimeters per minute. Okay, so I want to find dA dt. So I'm going to take this equation, my area equation in terms of its length, and I'm going to take a derivative of that with respect to time. So so the left-hand side is going to be exactly what we need. So if I take a derivative with respect to time of both sides, I get dA dt equals what? So kind of have a application of the chain rule here. This 6L squared I can think of as a function of L. So the first thing I'm going to do is to differentiate that with respect to L. So that'll be 12L. And then I'm going to differentiate L with respect to time, so that'll be dL dt. So I want to find dA dt. So I hope I know what L is, and I hope I know what dL dt is. So what does L stand for? We wrote this down. The L stands for the length of the edge of the cube. Do we know how long the edge of the cube is when we care about this? Yes. We gave that as 80 centimeters. So 12 times 80 centimeters. And what does dL dt stand for? Well, if L stands for the length of the edge of the cube at any given time, and T stands for the amount of time that has elapsed or gone on, then I think dLdt stands for a rate of change of that length with respect to time. So I'm going to say this is -2 centimeters per minute. So yeah, the problem says 2. Why am I saying -2? It's because it's calling it a decrease. So that's what I'm going to go on there. So our final answer is going to be numerically whatever 12 times 2 times 80 is. So 12 times 2 times 80 is -1,920 cubic centimeters, not cubic, square centimeters per minute. So that's how fast our surface area is changing over time. So that's part A. Part B asks us for how fast the volume is changing. So same object, same cube, but now I want to know how fast the volume is changing. So my surface area equation is not going to be relevant for this part. What is going to be relevant is a volume equation. So how do I find the volume of a cube? I take the length of any edge and raise it to the power of 3. So we have a new equation, but from here we're going to kind of follow the same process. So I want to know how fast the volume is changing. So instead of looking for dAdt this time, I'm looking for dVdt, which is what I'm going to get when I differentiate this equation, both sides of this equation, with respect to time. So what is the derivative with respect to time of volume? That's going to be dVdt. And what's the derivative of L cubed? So just like we did with our first part here, we kind of have an inner and outer function here. We have length, which is a function of time. We can think of that as our inner function. And kind of acting on that, we're cubing the length. So if we take the derivative using the chain rule here, our outer function is something cubed. So what's the derivative of something cubed? Well, the outer layer of that is going to be 3 times whatever the something is squared. So that comes from the power rule. And then the derivative of the inner function is going to be dLdt. So like we said before, I want dVdt. So I hope another length. So what hasn't changed since last time is I care about what happens at the instant when the length is 80 centimeters. And what is dLdt? We said before that is -2 centimeters per minute. And this comes out to be something I'll share with you very shortly. So 3 times 80 times 80 times 2. So I am getting a value of -38,400 centimeters cubed per minute. So that's the rate of decrease of our volume with respect to time. All right, moving on to question 2. So we have an 8-foot long ladder leaning against a wall. Okay, so I'm going to stop reading and draw myself a picture. So more bad art. Here's my wall. Here's the floor. I'm assuming a right angle. Here's my ladder. Okay, what do I know about this ladder? Actually, I'm not going to label anything yet. Let me keep reading. The top of the ladder is sliding down the wall at a constant rate of 2 feet per second. Okay, so let me get rid of these hashes that I had here. How fast is the bottom of the ladder moving along the ground at the point in time? Okay, so let's talk about our variables here. So I know that my ladder is 8 feet long. So 8 feet. The top of the ladder is sliding down the wall at a constant rate of 2 feet per second. Okay, so this sounds like I'm going to be paying attention to this distance here. It's vertical, so I'll call it y. But what does y stand for? So it's nice to have a name for that, but let's be really systematic and specific about what y is. I'm going to say that y is the distance from top of ladder to floor. And I'm going to measure that in feet. Okay, how fast is the bottom of the ladder moving along the ground? So that suggests to me that we also care about this horizontal distance. So what's that distance? That's the distance from bottom of ladder to the wall. And we're also going to measure that in feet. So and to be clear, the reason I've marked those distances are because that's what's in the question. The question told me the ladder was 8 feet long. It told me, or it suggested to me that the top of the ladder is something I care about, or the top of the ladder sliding down the wall. And it also suggests to me that I'm going to also worry about the bottom of the ladder moving along the ground. So those distances are the things I'm worried about. One more thing here, I'm going to call this thing Z, and I'll explain why I'm replacing that. So you can kind of look at this both ways. I'll kind of go back and forth to show you how to solve these problems in both these ways, but I think it's safe for me to just call this thing that I just labeled Z as 8 because I think we can safely assume this ladder's length is not going to change. So because of that, this hypotenuse of this right triangle we just made, it is always going to be 8. The things that are going to change are Y and X because that's basically as the ladder slides, those distances are going to change somehow. So I have my variables, and one thing I want to here, I haven't even looked at what I want to solve for yet. We could do that, but right now I'm going to focus on, okay, is there some kind of equation that I can make that'll wrap up all these quantities that I'm talking about? So let's talk about what Z is. Z is the length of the ladder. So is there some kind of equation I can use to join all of the variables or all the quantities that I'm talking about here? So I have a right triangle and I care about the distances of the sides of that right triangle. I'm going to go for the Pythagorean theorem. So x squared plus y squared equals z squared. So what can I do with this equation? So now is probably a good time to figure out what it is that I want from this. So let's read the question again. An 8-foot long ladder is leaning against a wall. The top of the ladder is sliding down the wall at a constant rate of 2 feet per second. Okay, there's a rate, and I know what that rate is. So the ladder is sliding down the wall at a constant rate of 2 feet per second. So this sounds to me like some rate with respect to time, but what the rate of what length with respect to time we talk about here? So the top of the ladder sliding down the wall. So y sounds like the way I've described y, the way I've defined it, that sounds like what I'm talking about here. The distance from the top of the ladder to the floor. So sliding down the wall, that's the distance that's changing here. So I think they're telling us that dy dt is equal to, and be careful here, not 2, but -2. So why am I being really specific about that -2? Well, because the ladder is sliding down the wall. So that means that the change in y with respect to time is going to be negative. The distance y is decreasing as time goes on. Okay, so dy dt is not what I want to find. That is something I know, something I have. All right, how fast is the bottom of the ladder moving along the ground? Can we give a name to that rate? So something with respect to time, I think that is dx dt, because that's what this distance here signifies, my x here. So I want to know how fast x is changing with respect to time, and I believe that is my unknown. Okay, so what do we want to do here? I have my equation, I have a rate, and I know what other rate I want to try to solve for. So here's what I'm going to do. I'm going to differentiate both sides of this equation with respect to time. So ddt of x squared plus y squared equals ddt of z squared. And all these terms are going to sort of act the same way. I can see them all as kind of like having this outer function of squaring something. So if I take the derivative of x squared with respect to x first, I get 2x and then dx dt. And for the same reason, 2y times dy dt equals 2z times dz dt. So here's one rate we didn't write down is dz dt. So what is dz dt? We can answer that by talking about what does dz dt even mean? Dz dt would mean what? So if z is the length of the ladder, then dz dt would be equal to, or it would represent the rate of change of the length of the ladder with respect to time. But we've kind of talked about this, the length of this ladder is not going to change. So because of that, this rate goes to zero. That there is no rate of change there. The length of the ladder is a constant. So one thing I want to point out here is that originally I just had this side as 8 feet. If you did have that as 8 feet, then instead of z squared here, you would have 64, which is a constant. And then as you take a derivative, that's going to go away. So that's one thing that kind of that I wanted to talk about when it came up was that sometimes you're going to realize that some of the quantities in your situation are not really variable. They're not ever going to change. If you're having any doubt at all, just treat them like a variable. And then you might get to a point where you realize, okay, that's not really a variable, but you're going to wind up in the same place. Okay, so let's keep on going. So we have, let's just rewrite 2x dx dt plus 2y dy dt equals 0. So I want to find dx dt. I know dy dt. I hope I know some of these other things too. So let's start filling in some of these details. 2x. Do I know what x is? So x is going to stand for what the length of the ladder is, or sorry, how far the bottom of the ladder is to the wall at some time. Do I know what that is? When the bottom of the ladder is 4 feet from the wall. So it sounds like I do know that that is 4 feet. What is dx dt? Well, we don't know. That is actually the goal here. I want that. All right. Plus 2 times y. What's y? I don't think I know. I don't know it. I'm not given it, but can I figure it out? I think I can because let me draw another triangle to kind of match this one here off to the side in our scratch work. I know this length is 8. No, this length is 4. So I think that gives me a way to find out what y is. So this is still a right triangle. Pythagorean theorem still holds true. So 4 squared plus y squared equals 8 squared. 16 plus y squared equals 64. Y squared equals 48. Y equals, for now, I'll just call it radical 48. We can do the rounding thing at the end. So 2 times radical 48 feet times dy dt. We said dy dt a while ago is -2 feet per second. All that equals 0. Let me kind of cordon this off. Okay, so I think we're off and running. So we're almost there because dx dt was the only detail, or like the only symbol in this equation that we didn't have a value for. So now we can do is this. So 8 feet times dx dt is equal to 4 times radical 48. I guess feet squared per second. So if I solve for dx dt, I get, and let's be real careful with the units here. 4 radical 48 feet squared per second over 8 feet. I'm going to attend to the units first. What's feet squared per second divided by feet? I think that's going to be just feet per second. So does feet per second make sense with this thing dx dt we're trying to find? Hopefully it does, because X is something that stands for length, which we're measuring in feet, and time is, or T is a measurement of time, which for this question we're talking about in terms of seconds. All right, so last thing to do here is round, or simplify or approximate. So what do I have here? I have radical 48 over 2, which comes out to be what? All right, this comes out to be approximately 3.46 feet per second. Last thing I'm going to say here is this is positive. Does that make sense? Hopefully it does, because as this ladder slides down the wall, that distance X is going to be growing. So I think at least for the sign, hopefully that kind of makes some qualitative sense there. Okay, so that's question 2. Moving on to question 3. So I have a tank of water in the shape of like this upright cone. It's leaking water at a constant rate of 1 cubic foot per minute. So that's useful. Cubic foot per minute. So it sounds like I have a change of volume over time. I'm also being told about the base radius of this empty tank, and the tank being 14 feet tall. So something to keep in mind here is those dimensions that have to do with the tank, those never change. But as the water level, or as the amount of water changes in this cone, um, what is going to change is, like, one thing that's going to change is how high the surface of the water is from the bottom, and also what the radius is. Like, if you think of like the surface of the water as a circle, the radius of that circle. So I'm going to draw another cone. And here's the variable I'm going to deal with. I'm going to draw a straight line, maybe. You know what? That's good enough. I'm going to call this thing H, and I'm going to call this right here R. And to be perfectly clear, H is, I'm going to say that's the water level. Not the height of the tank, but the height of the water in the tank. So that's going to be measured in feet. And what else do I need to know about? Oh yeah, the radius. So the radius. So I'm going to say that's the radius of surface water. That's also going to be measured in feet. And something that's kind of implied here is that I'm looking at a volume. So that's going to be, I'll call that capital V, volume of water. And if these lengths are measured in feet, then I'm going to say this is feet cubed. Okay. All right. So now let's do this. So to be clear, something I want to point out is I haven't even looked at what this question is asking us to do. So, and I think that's a kind of a good thing that I would encourage you all to do, is just start cataloging the information that's in here. It's probably all going to be useful, but just see what you have. And now let's look at question A here. At what rate is the depth of water in the tank changing when the depth of the water is 8 feet? Okay, so is there an equation I can use that joins all these things together? So I have the height of the rate of the water in this tank, the radius of the surface of the water, and the volume of the water in the tank there. So I know what shape this water is always going to make, and that's going to be a cone. So I'm going to write down the formula for the volume of a cone. So the volume is equal to 1/3. And by the way, I'm doing this from memory. You can absolutely, hopefully you've looked this up if you didn't remember it. So 1/3 pi r squared times height. Okay, so one thing that I think makes this question harder than the last two, or at the very least different from the last two, is we have 3 variables here. We have volume, radius, and height, whereas in this one we had Actually, I take it. X and Y were variables. Z was actually a constant. Um, in this one, we had area as a function of length or volume as a function of length. So this is the only one that has three really true variables. Volume, radius, and height are all things that change. So part A asks for what? At what rate is the depth of the water in the tank changing? So what rate is that? The depth of the water, we call that height, but that's kind of the same thing. I think for this one, we're looking for dHdt. So how do we find dHdt? So there's two parts of this problem. I'm gonna solve them two different ways. Let's say right now, okay, I have volume, radius, and height. I can think of them all as functions of time. So let's do this. I'm going to take a derivative of both sides of this equation with respect to time. So if I do that, the left-hand side becomes dv dt. The right-hand side is going to be a little more involved. I'm going to need the product rule because r squared is a function of time, h is a function of time. So how does product rule work? I need to find the derivative of this first function. Let's do this. I'll kind of absorb 1/3 pi. So my first function is 1/3 pi r squared. What's the derivative of that? So just like we did a couple times before, got to take a derivative of the outer function. So whatever the function is with respect to r, so that'll be 2/3 pi r. But then I'm going to multiply that by dr dt. Let's make that a little more legible. dr dt. And then the h will be unaltered, so times h plus, and then do the second part of the product rule. 1/3 pi r squared times the derivative of h with respect to time. That's dh dt. dh dt. Okay, so I want to find dh dt, which means I need a bunch of other details. So do I know what dv dt is? So that would be a rate of change of volume with respect to time. So do I know that? The water is leaking out at a constant rate of 1 cubic foot per minute. So I do know that. So now let's start filling in the details. -1 cubic feet per minute. So I know dv dt equals 2/3 pi times the radius. Is that something I know? Nope, I wasn't given that. But can we find that? So this is where we're going to rely on something. The fact that, so I think I said this before, but the water in this tank, no matter how much water there is, that water will always form the shape of a cone. Not only will it form the shape of a cone, it'll be a cone similar to the one, you know, it'll have to be the same shape of the cone that the tank is itself. So here's what I can rely on here. I know that if I treat this tank kind of like, we can look at it as like a similar triangle thing here. What does the empty tank look like? Well, it has a radius of 5 feet and a height of 14 feet. But the tank is not full of water when I'm asking this question. What I have instead is this. This might not be to scale, but it doesn't really matter. This height right here is 8 feet, which means the radius is going to be something less than 5. So how do we find that? So one thing we know about similar triangles is that these ratios are going to be the same. So the ratio of the height of the tank to the radius of the tank is going to have to be the same as the ratio of the radius of the water. Sorry, that 8 is the height of the water to the radius of the water. So if I solve this equation, 14r equals 40, then that means my radius is going to be 40 over 14. Can I reduce that a little bit? Just a little bit. So this is going to be 20 over 7 feet. Okay, so that was a long way to get to the radius that we kind of had to get there using similar triangles. Okay, but moving on. What is dr dt? Is that something I knew? No, we didn't, but here's what we can do. Um, we can also use that similar triangle information because so what do we know about the ratio of the radius to the height? The ratio of the radius to the height is 5 to 14, which means, so let me just write this down. Let me just write down what I said in words in math notation. The ratio of the radius to the height is going to be 5 over 14, which means that we can say what? 14r is equal to 5h. I'm going to redo this, give myself more room to kind of flesh out all my thoughts here. Erase, erase, erase. Be shy, erase. Or, okay, fine. Okay, so can I, yeah, so this is served its purpose. I'm going to get rid of this. So no matter where the water level in here is, the ratio of the radius to the height is going to be this. 5 over 14 is going to be equal to the ratio of whatever my unknown radius is to my unknown height. So if I cross multiply, I get what? 5h equals 14r. So 5 times the height is equal to 14 times the radius. That's true about the height and the radius, but if I take a derivative with respect to, sorry, the derivative of both sides with respect to time, I get this. 5 dh dt, make an h, come on, eraser. 5 dh dt equals 14 dr dt. And I'm looking for dr dt specifically, right? Actually, what was the thing I was trying to solve for here? Oh, trying to solve for dh dt. So because of that, I'm going to solve this for dr dt. So from here, I can say that dr dt is equal to 5/14 dh dt. So a couple things we've done here is that, or I'll focus on kind of the big picture here. The radius and the height, which this whole time I've been treating as two variables, are linked in this very like powerful way. So really, they're not two variables that are totally independent from each other. They're both governed by the same thing. And hopefully that becomes more clear when I kind of write this out. So dr dt for now, I'm just going to replace with 5/14 dh dt. And dh dt is the thing I want to find. Next thing I need is the height. Do I know, or h? Do I know what h is? Okay, we don't have to do that much work to find this. That's just 8 feet. That we are given that. So 8 feet. I'm going to move to the next line here. Plus 1/3 pi times the radius squared. Do I know the radius? Oh yeah, I already wrote that down. So that's 20 over 7 feet squared times dh. And so exasperate with this eraser. Plus d or times dh dt. Okay, so we filled in all the details here, and it might not feel like it, but we actually are pretty close to being done. So one thing I'm going to do here is to kind of basically, let's look at this. Where are unknowns? The unknowns are only dh dt. So once I do some kind of simplifying, I can solve for that. So let's do this. So -1 cubic foot per minute is equal to, let's just combine all these things together. 2 times 20 times 5 times 8. So 40 times 5 is 200. times 8 is 1600. So 1600 pi over 3 times 7 times 14. Actually, let's take it back. Let's start canceling and reducing things if anything is convenient for us. Now that I've said that, I don't think there's much we can do. So let's just, okay, contradicting myself, but that's okay. 2 times 20 is 40, times 5 is 200. 1600 pi over 3 times 7 times 14 over 294 times dH dt plus, okay, so now let's collect these things. So numerator, 1 times 20 times 20. So 400 pi over 3 times 7 times 7, 7 times 7 times 3, over 147 times dH dt. I kind of lost track of my units there, but that's okay. Actually, let's be really clear here. What are the units here? So I have a foot here, a foot here. That's feet squared. And then I have feet squared here. So luckily those match up. I can actually combine them. So this is feet squared. Let's do this to kind of stop having to deal with that. I have a foot squared on both sides, right? I'm going to divide both sides by feet squared. That'll cancel. This will just become feet. So now what I have is this. -1 feet per minute equals, let's do ourselves one more favor here. Actually, they have a really nice common denominator. 147 is exactly half of 294. So this becomes 1600 pi plus, now let's actually take the time and do this carefully. Oh, new denominator. Okay, so now what I have is this. -1 feet per minute equals 2400 pi over 294 dH dt. So if I divide -1 by that, basically what I'm getting is the reciprocal. So I get dH dt equals -294 over 2400 pi. So, and that's going to be in feet per minute. So let's get you a numerical number there, or numerical value. Okay, and that's equal to -0.039 feet per minute. So a long way to get there, but that is going to be the value for basically what's happening to the height of the water with respect to time. So we're going to do part B next, but I don't want to go around and do all the erasing there. So I'm going to jump out of this and open it back up. Okay. Okay, so now we want to look at something a little different. At what rate is the radius of the surface of the water changing at the same instant? Okay, so I'm going to do this, I was going to say a slightly different way, but I think it's going to actually look pretty different. So still sticking with the volume. Volume equals, what is it? 1/3 pi r squared h. But one thing I said as I was working through the problem for part A is that radius and height they don't vary independently of each other. they kind of go together. And one big idea that kind of came out of this was I drew this triangle, like this cross-section triangle of this cone. And one thing I want to say here is this: I'm going to label these sides 5 feet and 14 feet because that's what the empty tank looks like. But even though the water level can vary in there, it can be less than 14 feet. The ratio of the radius of the water to the height of the water will always follow the same ratio as the overall cone. So because of that, I can say this. The ratio of the radius to the height of the overall cone will be equal to the radius and the height of the overall water. So I can say this. I already did this, but I'll do it again. 5H equals 14R. I'm going to solve for height. Could really solve for either one, but I know the height will always be equal to 14/5 of whatever the radius is. Here's what I'm going to do here. And I'm going to suspect that most of you will find that this approach, like making this manipulation early, makes the rest of the problem a lot easier to deal with than the way I just went through A. So hopefully I've convinced you that the height will always be equal to 14/5 times the radius. So I'm going to do this. I'm going to rewrite this equation using that information. 13 pi times r squared times 14/5 r. So now I have an equation that only has a single independent variable. So let's yeah, let's just keep going. So if I simplify here, what do I get? I get 14 pi over 15 times r cubed. That's my volume. So that makes, so my equation looks a lot less involved now, but also that makes my derivative a lot easier to deal with. I'm not going to have to deal with product rule this time. I still have to deal with the chain rule, but dv dt equals the derivative of r cubed will be 3r squared. So this will be 42 pi over 15 times r squared dr dt. So now for part B, what is the thing I'm solving for this time? At what rate is the radius of the surface water changing at this instant? So I think that's dr dt. So dr dt is the thing I'm going to solve for. dv dt was the rate of change of volume with respect to time. That was given to us. That's a constant rate of -1 cubic feet per minute equals 42 pi over 15 times the radius squared. What is the radius? Do we know? Well, not really, but we're asking about what's happening at the same instant as the last problem. And in that instant, the depth of the water was 8 feet. So if the depth of the water was 8 feet, then what is the radius here? So we can solve this little equation based on this ratio I found. Multiply both sides by 5 over 14. I get 40 over 14 equals r, or 20 over 7. That looks familiar. I think we found that last time. So equals 42 pi over 15 times 20 over 7 squared times dr dt. So all we have to do really is basically divide out and isolate dr dt. So this time I'm going to play a little more fast and loose with the units because I'm going to trust that they're all going to shake out because I feel like I've been careful up to this point. What's 42 times 20 times 20? 42 times 20 times 20. So 16,800 pi over 105 dr dt, which means that dr dt is equal to -105 over 16,800 pi Feet per second. Let me give you a numerical value here and we'll call it a day. So pretty small number, negative 0.00199 feet per second. All right, so that is all for checkpoint number 9.